Hey everybody. This is day 17 of the June Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. And today we have a hard, so yay, but it's, okay. I was going to wait to reset it because it is 34:05. It's always a little bit weird whether it's in my cache or not. Seems like we did solve it, so that's good, but let's take a look. Let's think about today's problem. Today, just quick exercise update is that I took a little bit light. I just did a couple of sets of squats and then a lot of mobility work. So hopefully that's good. I don't know. I'm debating whether to do a 50K on Thursday, so like a couple of days. Obviously, if I was training for it, I would have trained for it. But and don't get me wrong, it's going to be a very slow 50K, 50 kilometers, in case you're wondering. So about 33 miles. We'll see. We'll keep you updated. If I do it, you'll see it for sure. So yeah, just doing a little bit of an outro, trying to get it out of the way this year. All right, let's take a look. We have 3405, count the number of arrays with k matching adjacent elements. You're given three integers n, m, and k. A good array of size n is defined as following. Each element array is inclusive 1 to m. Exactly k indexes satisfies the condition arrays of I is equal to I, okay? Return the number of good arrays that can be formed. Since the answer can be very large, return mod. All right, let's, remember the mod. Okay. My first instinct is probably going to be some sort of dynamic programming, but n and m is being 10 to the 5th is pretty big. Well, maybe we consider that for a second. Okay, so what I think these problems you have to kind of think about how to reduce them to a problem that you can understand, at least for me. Okay, so we have n numbers, right? So this problem is saying that we have. Let me put together. We have, and I like them to be caps. We have. Okay, so I think for these problems, it's kind of interesting to kind of think about the upper bounds and lower bounds, and just and what I mean by that is just like removing some constraints so you could solve some of the subproblem. Not going to work every time, but or maybe you can make some progress at least, right? But we have n numbers, each number from 1 to m, and that's really it. And then there's this k thing. K indexes where they match. Okay. Exactly k, in fact. Yeah, okay, so let's say without the, let's ignore this part for now, right? The k index part, then what should it be? Well, the n numbers, each of them from 1 to m, so there's m parts to the n, right? So m to the n is going to be an upper bound. I say that just because, if you want to sanity check, if you get a number that's bigger than this, then it is probably wrong, right? Or it is just certainly wrong, actually. But yeah, and then now we have k indexes part, right? I, right? And of course, I cannot be. Is this not equal to the last element? I know this is I minus 1 is equal to I, but that means that. I guess maybe that's fine. I don't know. Indexing is kind of tricky. But it means that what is k? Okay. So what does k indexes mean, right? The way that I think about this condition is just that you're almost deleting a number, right? That's the way that I would think about it. Because if they equal to the same, then you delete a number in the sense that you lost 1 degree of freedom, right? Meaning that if the number before is 5 and you choose this index, then this number is also going to be 5. So in effect, you're removing one number without needing to, in this case, multiply it, right? So maybe this isn't quite right because you have to choose which k index, but you could already imagine that now it's just going to be, we used to have n numbers, but now we actually have n minus k numbers, right? Maybe k minus 1 or something. But either way, like something like this as a new upper bound, right? But again, now we have to choose, well, which k index is, right? And I have to be precise about this. Maybe I'm off by 1, but it's going to be similar, right? But let's say we have n numbers. So then that means that we have, let's just say A, B, C, D, E, F, G. I don't know. Yeah, maybe avoiding that other notation. A of 0, A sub 1, A sub 2, A sub 3, A sub 4. And the space is just whether it is equal to the previous number, right? And given that we have k indexes, that means that given n numbers, well, let's say in this case we have 5 numbers, how many spaces are there to choose? And in this case, you could say spaces, but also just like one of the numbers to remove, right? And we cannot choose the first one to remove without loss of generality. That means that we have to choose one of the other ones. That means that given n numbers, we have n number 1 numbers. We have to n one slots, maybe. I don't know if that's a better word. And choose k amongst them, right? Amongst. So already, and then what happens? And then now, after we choose, I'm trying to think whether this is true. In combinatorical, by the way, combinatorics, there are a lot of different ways of coming at the same thing. So I'm just trying to think whether, yeah, what is the easy way of doing it? And yeah, so then now you have like you could even write them as like equal or not equal or so forth, right? Because, and just to be clear, when you choose these, that means that the next number has to be not equal, right? Like there's no choice. So, and what I mean by that is that it's not quite this. So I was wrong or imprecise earlier when I said that when we choose a number to be equal, that means that we have no choice here anymore. We remove a degree of freedom, and that's it, right? But that's not quite true in the sense that the next number has to be not that number. So in a way, and then the tricky thing about this is that, but in this case, you can think that, I don't know, we leave it open for now. If A3 is equal to A4, then everything afterwards is, or because there's nothing afterwards, then there's no choice. So I have to think. So we have to do the counting that way. And because the way that I would have said, if my earlier imposition was correct, in which you can just remove them, treat them as remove, then now you can say this is just, well, m to the n of k, actually, right? Because it almost doesn't matter which one you remove. Well, no. Actually, it does matter, but so then now for each combination, it would be this times n minus c for choice, n minus over k, right? Or something like that. So I think this would have been how I imagine it. But that's not quite right? Because m, the first element is going to be m. Let me write it back in. The first element is going to have m choices. This one either has, if it's equal, then it has no choice, or one choice rather. Otherwise, in this case, this is m minus 1, right? And this is m minus 1. Because this one also has to be either equal or not equal to this one, which means that it only has m minus 1 choices. So then now, maybe this is fine. I don't know if this is right, because honestly, combinatoric stuff is hard, right? So m minus 2, n minus k minus 1, right? Maybe? Because there's n minus 1 of them, and then minus k because k of them are equal. I want to say this is good, but honestly, this is one of my weaker stuff, combinatorics. I feel like this passed the smell test. I'm trying to think. Yeah, I'm trying to think whether that's true, and it almost doesn't even matter where you do the plus or minus or the n choose k. I think this is right. So then now we have to kind of come up with this one, right? So here we have m times this thing you want to mod pow, right? So pow of n minus 1 to n minus 1 minus k mod. We might have to do some check on. Okay, I was gonna say we have to choose n and k, but I think that's fine. And then so it's this times choice. So at this point, I know that this will overflow, right? But I want to just at least see, even because I mean not overflow. Sorry, I mean it overflows for sure, but also it will just be very slow. Is the more important part. But for the inputs, it should be good if it is good. So that's why I wanted to take a look. Random dot. Oh no, not true. What is that math? Combinatorial comp. Maybe I was confusing functions. But yeah, the reason why I checked this is that for bigger numbers, it's possible that it's either wrong or too slow, or not wrong, but just too slow because it gets too many digits to calculate. But I just want to see, basically if this is wrong for one of the examples, then it is definitely wrong, right? It doesn't, you only need is one case where it's wrong. But if this is good, then at least it gives us an attempt to kind of figure this out, right? Okay, we could. I'm not gonna lie. I'm gonna YOLO submit right now just to kind of show you how it may time out, and may time out because okay. Well, I can't even force a timeout apparently. All right. Well, thanks for watching. No. We'll do it the quote unquote the right way because this doesn't work in other languages, and apparently this is early in the year. What did I do? Okay, I mean, okay, I shouldn't have spoiled it. All right, well, I mean, maybe I did it another way, but this part, right? This is game theory, or not game theory, sorry, number theory stuff. And basically, if you know your math, and sorry that I went a little bit faster, right? Because this is just you have n minus 1 sides, choose k. This is n minus 1 choose k. And n minus 1 choose k, which I didn't go over because I wasn't sure that this is correct, so I didn't go over it because I was like, well, if it's wrong, then I don't want to go, It's equal to n minus 1 factorial over, in this case, k factorial times n minus 1 minus k factorial, right? And this is also a definition that you could read in a book. You can definitely prove it as well, but I think this is, I would consider it prerequisite, right? Okay, so then now how do you solve this part? I mean, this part in theory is not that hard. The hard part is that we have a mod, right? Because we have a modulo, right? This is mod, or this is easy to mod. This is easy, or this is already modded because that's just mod power. But you can actually also implement this yourself relatively easy. It's an intro to repeated powering, repeated doubling, repeated something, exponentialization, right? Fast exponentialization. But here, the thing is that okay, well, and n minus 1 factorial is easy to calculate with mod because you just multiply everything. But then divide. What does division means under mod? So this is where you have modular inverse, which is roughly speaking, I mean there are more formal ways to define it, but roughly speaking, is equal to division under mod, and what that means is that, for example, you think about two variables a divided by over b over some mod, right? Is equal to some number c, also under mod. It's not quite the right notation, but I'm using ASCII art, so right. So given this definition, the way that you can redefine the modular inverse is that it's just the number in which a times b to the -1, because is 1 over b, but this is the modular inverse. Basically, you're trying to find out this number. So I'm not going to go over how you calculate this, but basically, instead of dividing, you're trying to find out a number in which this is the inverse of it is equal to c, right? So that in a way, like for example, if this a is b, then b times the modular inverse is equal to 1, right? Because it's same as b over b. So a lot of stuff like that is, I know that I'm hand wavy here because this is definitely a more in-depth topic, but if you are interested, then look at modular inverse. It turns out, in Python there is a library for it. The more you can figure out the math with GCD with the extended order function. Not going to go into that much, but the way that I would construct it is that, okay, well, we have n minus 1 factorial, so that's easy to construct, right? So 1, right? So for I in range of, and then we'll maybe go to the max number, which is 10 to the 5th, right? Okay, yeah, let's just go to max. So okay, right? So then fact dot append factorial minus 1 times I, and we have to start at 1. Mod, right? So this is straightforward-ish. So then the inverse of this, and that's just how I would figure out. I write ifact for like inverse factorial, so that instead of saving, so then it gives me two things, right? Or factorial on the mod will give me fact sub I is equal to I factorial mod, and then I fact I is equal to 1 over I factorial, right? And that is, given that this is factorial, we can just do 1 over, right? So we append the last number, and actually you can do this to I think this is the syntax, but in Python this is the library. You could use pow to calculate it, and as a result, then now you have factorial and I factorial, and then now you can rewrite this as, same as here, which is factorial of n minus 1 times I factorial of k times I factorial of n minus 1 minus k. And that's it. Run it real quick. Quick submit. Maybe it times out because there's an optimization that I could do, but I just wanted to show you how this would be done. And yeah. Oh wait, no, it's still going. I saw accepted, so I did. But it's time limit exceeded, which is actually a little unfortunate. The reason is because we're doing it to max every time, so maybe that's just a silly. But one thing that you could do in Python is that, well, I guess you could actually convert it to n. Yeah. Give it submit real quick. There's another optimization that I was going to do. That's why I wrote it that way. But I'm curious whether this would be fast enough. Because this is Leetcode, and that's why Leetcode is kind of dubiously crappy. It works, but it takes 9.7 seconds, just barely. And the way that I was going to say is that, given that we reuse this function and the answer does not change every time, you can actually just put it outside the loop. And it is a Leetcode specific thing. Well, not depending on how you want to say it, but it is definitely at the very least Leetcode specific, and it basically just does order calculation at most once, right, over all the solution cases. And see, this is 9.7 seconds, and you can see that it goes immediately to 4 milliseconds. So yeah, and you can even like be a little bit smarter about this, because it is just, yeah, but it's fine. But yeah, and that's it. That's all I have for this one. yeah, so this is the factorial and inverse factorial, and here's the formula, and we went over the formula. So yeah, and this is all lookup of O of 1, well, except with this one. This one is O of, it's linear in the size of bits. So given the number n minus 1 minus k is the number of bits representing that, which is another way of saying log of n, if you will, is an upper bound, which is at most like, what, 32? No, not even. It's 10 to the 5th, so that's like 17 or 18 or whatever, right? So yeah, and everything else is just multiplication and then a mod at the end. Using other languages, you might have to mod more often, etc. You have to prove your bounds a little bit, but that's basically the idea. And yeah, and that's all I have with this one. Let me know what you think. Interesting problem, but yeah, thanks for watching. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.